Welcome to The Explainer, where we break down the big ideas that shape our world. Today, we are diving into a concept that honestly made the modern internet possible. We're talking about MapReduce. Have you ever really thought about that? I mean, how can any system possibly sift through trillions of web pages almost instantly? The answer isn't some mythical supercomputer. Nope. It's a revolutionary way of thinking about how to handle just an unimaginable amount of data. All right, so to really get the genius of the solution, we first have to wrap our heads around the sheer scale of the problem they were facing. I mean, think about it. Even the beefiest computer you can imagine has its limits. You're going to run out of memory. You're going to run out of processing power. When you're dealing with the entire web, you hit those limits like a brick wall almost immediately. So the only way forward is to link up thousands of computers to work together. But as you'll see, that solution creates a whole new world of problems. And this is where things get kinda wild. You're not using a handful of super expensive, super reliable machines. You're using thousands and thousands of cheap, off-the-shelf computers and hard drives. And when you have that many parts all whirring at once, the math is pretty simple. Something is always broken. Failure isn't some rare event you have to plan for. It is happening constantly. It's the norm, so your system has to be built from the ground up to just expect and handle failure gracefully, all while trying to shuffle massive amounts of data between all these machines. So yeah, the old ways of doing things, the programming models built for one reliable computer, they just won't cut it. Not even close. We needed a totally new way of thinking. So before MapReduce showed up and changed the game, what were people doing? I mean, there were already some really powerful ways to do distributed computing. Let's take a quick look at the main players on the field at the time. You had some great options, but they all had major trade-offs. On one hand, you have multithreading. It's fantastic for parallel tasks, but it's all stuck on one machine, so you're limited to gigabytes of data. Then you have something like MPI, or a message passing interface. It can handle terabytes of data across a whole cluster, but its fault tolerance is really low. One machine goes down and your entire job could crash. And then there are GPUs, which have their own set of pros and cons. For instance, look at GPUs. They have this incredible parallel processing power, right? We're talking thousands of little specialized cores compared to a CPU's handful of really powerful ones. But actually getting them to do what you want for general data processing, well, that can be notoriously difficult, requiring some pretty complex low-level programming. So the stage was perfectly set for a new approach, one that was built from the ground up to work on massive, unreliable clusters of what we call commodity machines, which is just a fancy way of saying, standard, inexpensive computers. And then MapReduce enters the scene. And its core idea was a total flip of the script. Instead of trying to bring all that massive data to one central computer to be processed, which is incredibly slow, MapReduce said, hey, what if we bring the computation to the data? And here is the elegant genius of it. Every huge, complex, scary data problem gets broken down into just two simple, repeatable steps: map and reduce. To really get what that means, let's use an analogy. Okay, imagine your big data problem is this. You have to count every single word in a giant library full of books. I mean, that's a pretty impossible task for one person, right? You wouldn't even try to read every book yourself. What would you do? You'd hire an army of assistants. And in the world of MapReduce, that's exactly what happens. We just call those assistants mappers and reducers. The mappers do the first pass, and the reducers come in later to consolidate all the results. So here's how it would work. First, the whole library of books, our input, is split into smaller chunks. Let's say we give one chapter to each assistant. Then comes the map phase. Each assistant, or mapper, reads their chapter, and for every word they see, they just make a little note, a little pair, like the, one, and one. Next up is the shuffle. This is where the system automatically collects all of those little notes and groups them together by word. And finally, you have the reduce phase. A different set of assistants, the reducers, gets assigned one word each. They take the huge pile of ones for that word and just add them up to get the final count. Okay, but we have to talk about this shuffle phase because this is where the real magic happens. As a programmer, you don't have to write a single line of code to figure out how to get all the counts for the word dragon from 100 different computers all to the same place. The MapReduce framework handles all of that messy, complex data shuffling for you. It's this huge, automated sorting job that just works. So this entire flow, from splitting the data to running all the map tasks in parallel to shuffling everything, running the reduced tasks, and spitting out the final answer, all of it is managed by the framework, hiding the really gnarly, complicated details from the programmer. Now, the technical process is really clever, for sure. But the true genius of MapReduce, the reason it completely changed everything, boils down to two things: simplicity and resilience. First off, it made programming for a cluster of thousands of machines incredibly simple. As the programmer, you only have to worry about your specific problem. You just write two simple functions: what to do in the map step and what to do in the reduce step. That's it. The framework handles everything else: all the parallelization, all the data distribution, and, most importantly, handling failures. And that brings us to the most crucial point: the built-in fault tolerance. Remember how we said failure is the norm in these systems? Well, the MapReduce framework is constantly watching every single machine. If a computer running one of your tasks suddenly dies, poof, gone. The system just says, okay, no problem, and reassigns that exact same piece of work to another machine that's free. The whole job just keeps chugging along as if nothing ever happened. This automatic recovery, that's the secret sauce. That's what made it so powerful. This quote from the original Google research paper just sums it up perfectly. It let developers stop worrying about all the messy, low-level details of distributed computing and just focus on solving their actual data problems. This elegant idea was the engine that powered Google's web index for years, and its core principles, simplicity, fault tolerance, they inspired an entire ecosystem of big data tools you've probably heard of, like Hadoop, and you can still see its DNA in modern frameworks like Apache Spark. It fundamentally made the scale of the internet that we take for granted today even possible. And really, that's the big takeaway from MapReduce. It proved that you can solve enormous, mind-bogglingly complex problems by hiding all that complexity behind a beautifully simple interface. It tamed the chaos of big data. And it's a powerful reminder that sometimes the ideas that really change the world are the simplest ones. Thanks for watching.